This is part 3 of the video series. You now have collected raw data from 2 experiments. You still have a long way to go. Now you need to take that raw data and calculate the data values that are the overall objective of the experiment. First, your handwritten raw data must be converted into digital form. For this experiment, you'll be using Excel. Second, once the raw data is entered into the spreadsheet, you need to add all manufacturer's values, any required constants, and perform required calculations. Third, you will plot the data and use the Excel trendline capabilities to determine the slope of your experimental curves. And finally, you will perform analysis of the goodness of fit of your experimental results by comparing your values against the manufacturer's data for the components used in the experiment. So first, we're going to build a spreadsheet from raw data. You should have handwritten data sheets for both the spring experiment and the thermistor experiment. Your data collection form may have been computer generated, as you see in this slide, or it may be completely handwritten. These raw data sheets are important for a number of reasons. They provide evidence that you actually performed the experiment. They protect your intellectual property, also called IP. Properly recorded and stored raw data in a research laboratory is usually recorded in a special laboratory notebook with numbered pages. As notes and data are recorded in the notebook, the pages are dated and initialed by the investigator. You may think that this is silly or overkill, but I'll give you just one example to illustrate how important this can be. In December 1985, the French Pasteur Institute filed an international lawsuit on behalf of their researcher, Dr. Luc Montagnier, against the U.S. National Cancer Institute's researcher, Dr. Robert Gallo. Both AIDS researchers claimed that they were the first to develop a test to detect antibodies to the AIDS virus in 1983. The hysteria and fear surrounding an AIDS diagnosis in the early 80s was much greater than what I have witnessed over the current COVID-19 global pandemic. In the early 80s, a diagnosis of AIDS was a death sentence. Nobody had lived longer than 5 years after a diagnosis of AIDS at that point in time. The lab that would get credit for the development of a diagnostic test for the AIDS virus stood to earn vast amounts of money. Just look at how many different labs have been working on diagnostic tests and vaccines for the COVID-19 virus in the first half of 2020. Ultimately, the court decision came down to the laboratory notebooks. There was a difference of 30 minutes between the notes in the laboratory records that indicated that the French researchers had, in fact, developed their test first. 30 minutes. These handwritten notes also provide you with a backup of your digital data files in case they become corrupted. So while some of you may be tempted to take a screenshot of my experimental data for your lab reports, keep in mind that you will be required to provide copies of your handwritten DAQ sheets in the appendix of your lab report. If you looked closely at each of my DAQ pages, you would have noticed that I have my initials written on each page. You must perform the analysis of experimental data that you collect. Do not ever discard your raw data. You must retain your raw data sheets, and you must include the raw data in your spreadsheets that you submit. When you open a new Excel spreadsheet, double-click on the tab at the bottom of the spreadsheet and change the spreadsheet name from Sheet 1 to something descriptive, indicating that this particular sheet contains the raw data typed directly from your handwritten sheets from the spring experiment. Save your spreadsheet. Do not make any changes to this sheet. You will copy the data over to a second sheet that will contain your calculations. Thus, if you have any accidental deletions or modifications to your raw data, you can simply recopy these columns into your calculations spreadsheet to recover. For a professional appearance, you then need to provide column headings with units in parentheses, and you need to format columns of numbers with the same units so that all numbers in the column have the same number of digits after the decimal point. Following is a quick video demonstration of the 3 operations highlighted in red. Here's a quick demo of some of the actions recommended on the previous slide. First, I'm going to go down here and double click where it says Sheet 1, and I'm going to give it a more descriptive name. This is my spring experiment. You could call it Experiment 1 or Spring, something that indicates that this is the raw data from the experiment. Then you're going to want to go up to your column headings, and one thing you might want to do is click on the home, select bold, center it, wrap the text, and then you'll want to do something, perhaps this line is the incremental mass, and that was in grams, and the word incremental doesn't fit on one line, so I'm going to widen this up a little bit so it's neat, and then I might want to increase the number of spaces after mass so that my grams winds up on a line of its own. So you put a description and then you put the units in side parentheses. And then the third item that's very important, you'll notice that they don't have the same number of digits after the decimal point. That's very unprofessional looking. So when you're trying to get something that's going to look neat and professional, you want to change it so that it will, all the data in that column that all have the same units, have the same number of digits after the decimal point. You will repeat the process with the data from the thermistor experiment. You'll add a new sheet to your spreadsheet. And again, you'll double click on the tab at the bottom of the spreadsheet and change the name from Sheet 2 to something descriptive, indicating that this particular sheet contains the raw data typed directly from your handwritten sheets from the thermistor experiment. Save your file. Do not make any changes to this sheet. You will copy the data over to another sheet that will contain your calculations. One item of note for when you are formatting your spreadsheets for professional appearance: if you need to use special characters such as the degree symbol and the ohm symbol shown circled here in red, this is how you do it. I need to add units. Under temperature, right here, I need degrees C. And since degrees is not on your normal keyboard, you would click Insert, and then Symbol. Find your degree in your symbol characters display, and then you close that. So now I have my degree, and then I just type, AC. Well, that's not working. C after that. Okay, and then the thermistor resistance is kiloohms, so a lowercase k is a symbol for kilo, and then we need the symbol for ohms, which is the Greek letter omega, And here it is, Greek capital letter omega, insert, close. So now that's how you would insert a special character. Now that you have entered your raw data into a spreadsheet, you're ready to perform the calculations necessary to allow you to achieve the objective of the experiment. The first order of business is to copy your raw data sheet into a second sheet that you will use to enter all your calculations. This provides a backup of the data you just typed in case you made an error that corrupts your data. Before you start entering formulas, first think about the variables with a single value that you will need to use repeatedly in your calculations. If you type that single value multiple times in calculations throughout the spreadsheet, what happens if you need to change that value? You have to remember to change that value in every cell of the spreadsheet in which it occurs. If you want to prevent possible errors, enter that number in a single cell and then use absolute addressing in your calculation formulas. Then, if you need to change the value of the constant, you only have to change a single cell and it propagates instantly throughout the spreadsheet. In the following video clip, I'm going to demonstrate this part of building the calculation spreadsheet for the spring experiment, and I'm also going to show you how to use the merge and center button and other ways to neatly and professionally format your spreadsheet. What you see here is the raw data in my spreadsheet. I'm going to select this box and it highlights the entire spreadsheet. And then I can either click copy, and notice you'll have that scrolling dashed line around all your cells. Then I'm going to go to my blank sheet, which is currently called sheet 3, and I'm going to click paste while keeping my source formatting, and I'm going to paste that here. Then I'm going to change my sheet number by double-clicking on the word sheet 3 on that tab, and I'm going to change this to a descriptive title. You can use your judgment for that. The first thing I want to do is I want to actually add a row. So I'm going to go over here and click Insert Sheet Rows because I want to segregate or designate those regions of my spreadsheet, my calculations sheet, that contain the raw data versus the constants versus the calculations that are performed on each of the raw data elements. So I'm going to, once again, I'm going to hit bold, and I'm going to center it, and I'm going to type raw data. But I want to center my raw data over all of these columns, A through E. So I will left click in my A1 column and drag to highlight A1 through E1, and then I go over here to this merge and center, and now you can see that my raw data designation is now a single cell over all 5 of the columns from my raw data sheet. Then I'm going to take 2 columns and I'm going to call that manufacturer's data and constants. And I forgot to bold my entire row, so I'm going to hit bold. This is going to be centered over two columns. And I'm going to make this one, I'm going to make F a little bit wider, and I'm under this, on row 2, I'm going to write description and units and value as my column headings. So because these are just single values, and I need to change this a little bit. Okay, now, first thing I'm going to do is I'm going to type an underline. And I'm going to want to highlight each of these values, each of my descriptions as bold. And then I'm going to type, first thing we had on the data sheet was load. Minimum load was in pounds force. And that was 0.7 pounds. And the maximum load in pounds force was 7.5 pounds. I don't need to further format these two values because they have the same units and the same number of decimals after the decimal place. They already look nice and professional. I'm just going to center them in the column. And then I've got spring rate, which is pounds force per inch, and that value is 2.6. And I'm also going to center that in the column. So those are the important values you need from the manufacturer's data sheet that I showed you earlier in the video series. Now I'm going to underline another cell, and this is going to be constants that I'm going to use. So my measurement is mass, but I need to get to force. So I need to multiply mass times gravitational acceleration, which is g, and that is in meters per second squared. Now, what is wrong with this? I really don't like it when you use this exponentiation. What I'm going to do is I'm going to show you how to take this 2 and I'm going to go up here to my menu. I'm going to click on that arrow under the font section, and I am going to select my superscript effect, and now I have meters per second squared properly and professionally formatted. In meters per second squared, this would be 9.81. I also have grams that are going to be multiplied times meter per second squared, and that will give me force in newtons, but I need to convert to pounds force, and you'll want to put that value there. You can get that off your calculator. If it has unit conversions, you can Google conversion websites to get the value. The value that I looked up was 0.224809. And then my conversion factor for centimeters to inches is 0.393701. Now you're ready to perform the required calculations on all your raw data. You'll want to set up appropriate column headings similar to what is displayed in this image. You may have noticed that the formulas appearing in columns H through L in row 3 look a little bit different than what we've seen before. That is because I pressed the Control key while pressing the key just to the left of the 1 key on my keyboard. That's the one with the squiggly line called a tilde on it. By toggling Control-tilde, you can change between the display of the actual formula that you typed into the cell and the display of the calculated number. Here I've enlarged the formulas that I used. Note that the cell addresses with the dollar signs are the absolute cell references. The cell addresses without the dollar signs are relative cell references. When I copy these formulas down the spreadsheet, the relative cell references will be modified, but the absolute cell references will remain the same. Once you have the formulas entered in the first row of data, left-click and highlight the cells with your formulas. Hover your cursor over the lower right corner of the highlighted region. Left-click when the cursor changes to a black cross, then drag that region down the spreadsheet to copy the formulas down. When the formulas are copied, notice again that the row numbers in the relative cell references were modified, but the absolute cell references remained the same. At this point, you are ready to toggle back to the calculated values using Control-tilde. Make sure the columns containing the calculated values are formatted properly. You will go through a similar process to perform the required calculations for your thermistor experimental data. I will leave it up to you to generate a properly formatted spreadsheet with the appropriate calculations using the raw data from that experiment. Once you have completed these calculations, you are ready to plot your data. Just to review, a plot is much more than a colored line drawn on a set of axes. A plot requires a descriptive plot title, descriptive axis labels, including units if applicable, and a legend should only be used when there's more than a single trace on a figure. If there's only a single line plotted on a figure, never ever use a legend. If you are plotting y equals mx plus b, the convention is that the independent data is on the x-axis and the dependent data is on the y-axis. What does this mean? Okay, again, you're plotting y as a function of x. Then you can also refer to y as f of x. You will commonly hear this type of plot referred to with the dependent variable first and the independent variable second. Now you need to look at what needs to be plotted. The first plot is just going to be a scatter plot of your raw data, but what goes on the x-axis and what goes on the y-axis. Remember, the formula was force is equal to the spring constant or the spring rate times the extension of the spring. So spring rate has units of pounds force divided by inch. So that means on the y-axis you've got pounds force and on the x-axis you have inches. So I am going to move my plot over. So I'm just looking at my data. I'm going to click on Insert and make sure you select an XY plot, a scatter plot. And I'm going to select just the data points without any lines between them because we just want to look at the raw data with this figure. Now I'm still under chart design, so I'm going to click here on select data and I'm going to add my data series. So again, the X values will be the spring extension in inches, and the Y values are going to be the force in pounds force. So what does that give us? Okay, now we have a plot, but we're not finished. First thing I'm going to do is format my axes. So I'm going to go down to the bottom and click on the axis labels until I get a little box drawn around the axis labels, and then I can right click and select Format Axis. I don't need to change a whole lot here, but I wanted to show you a few things. If I were to need to plot anything on a logarithmic scale, this box right here is where you would select that. That's going to be something you're going to need to know for your thermistor plots, not for this one. I want to format my number because I have way too many decimal places. Just a single decimal place on the axis label is adequate in this case. All right, so now I've got nice labels there. I need to format my y-axis. And I want that to be 1 digit also. But I also want to move my numbers so that they are outside of the plot. So the way you do that is to select Labels, and the label position is going to be low rather than next to axis. So now I have my labels moved outside of my plot box. And now you can see the data, just the raw data that was collected. But I also need to add some very important chart elements. The first is the title. This is going to be Figure 1. Force versus extension, all data points. Something descriptive. Then we need to add our axis labels. Primary horizontal is going to be extension in inches, and axis titles primary vertical is force in pounds force. Okay, that's easy. The reason I wanted you to plot this, all of your raw data, is so that you could visualize the nonlinear quality. I wanted to show you the nonlinear nature of this spring. Remember when we were talked about it, there was a minimum force and a maximum force. So the minimum force means that below that minimum force, which was 0.7 pounds force, the spring will not extend. And we are seeing that on this plot, we're not getting any extension for forces below 0.7. That's great. I don't need this circle anymore. Okay, now I'm going back over here. I've moved my Figure 1 off, and I'm going to insert another scatter plot. And I'm going to move it over a little bit. Now for Figure 2, instead of plotting all my data points as I did in Figure 1, I want to only select those plots for which force is greater than 0.7. So these first 1, 2, 3, 4, 5 data points will not be included. This isn't just a matter of changing the maximum and minimum on our y-axis. You want to only select those data points that fall between the minimum and maximum load. So I'm going to select my data, and I'm going to add. So here is, I'm going to start at line 8 and my X data. is here, and then my Y data starts at line 8. Okay, so now we're just going to have the data that we want to calculate our slope from. Again, before you go any further, you're going to want to format your axis. I don't need to move my labels outside of my plot because I don't have any values at 0 or below 0. So I need to add my chart elements, my chart title, figure 2, force versus extension, and this is the trend line calculation plot. And the axis title, horizontal, is extension, and vertical is force in pounds force. The reason I made this plot over again from scratch is to make sure that you don't simply copy for a figure 1 and then just change the amount of the x-axis that you're displaying. I only want those data points that I want to calculate the curve from. Now I've got my curve. I want to highlight all this data, and I'm going to add a trend line. I want a linear trend line, but I'm going to go down here to more trend line options because I need more than just the trend line. I need the formula for the trend line. So I need to display my equation on the chart. I need to display my R² value on the chart. So you select those two radio buttons, and now you can see I have a formula for my curve and I have my R² value. Now that we finally have our experimental results, let's assess goodness of fit. On this Excel spreadsheet, I have added and formatted an additional 2 columns on my spreadsheet. Now I'm going to go into my equation and I'm going to copy. You can't do Control-C, you can only click on copy at this point, and then paste. So I'm going to copy that value, and then I'm going to get my value from the formula or the equation. This is actually the y-intercept, which translates to the minimum load. So I want to see how close we are to that. And then I'm going to go and I'm going to copy the R², copy and paste. And I can probably take these down to 2 decimal places and centered. And I'll take this one down to maybe 3 and also center it. All right, so the spring constant is the slope of the curve, and that's 2.86 approximately. And if I go back over here, 2.6 is what the manufacturer stated. So what we have to do is go to our error calculation, and the error from the formula that was given on the lab handout is the experimental value minus the given, which is the manufacturer's value, divided by the manufacturer's given value times 100. That will give us percent error. And for minimum load, similarly, it would be the experimental minus the given divided by the given times 100. And I'm going to change that to number and center. Right, so what we're looking at is the spring constant. I had a 10% error. That's very good for an experiment such as this without extreme accurate measurement tools and multiple repeats of the experiment. And the minimum load, the 7.7 pounds, I was only 2% off from that, or 2.5% off. This is very good results. And then finally, when you're talking about goodness of fit, the R-squared ranges from 0 to 1. If there's absolutely no correlation between the two sets of data, between the data on the x-axis and the data on the y-axis, you'll get an R-squared closer to 0. If you have a very, very good fit to a linear equation in this case, it will be closer to 1. So we're wanting to have a correlation closer to 1, and we wound up with 0.992, which is extremely good. So we have a very good fit of our experimental data to this linear equation. This concludes the video series on the Digital Acquisition Lab.